The final two inference rules that we are going to introduce today are biconditional introduction and biconditional elimination. Biconditional elimination is very, very similar to conditional elimination. The basic idea motivating this rule is this. If you know that P, and you know that P, if and only if Q, then you can infer Q. So for example, if you know that Alice did great in the exam, and you know that Alice is happy if and only if she did great in the exam, then you can infer that Alice is happy. This rule is also called biconditional modus ponens. So here's the formal statement of biconditional elimination or biconditional modus ponens. If in line M of your proof, you have a sentence of the form A, and if in line N of your proof, you have a biconditional, where one of the sentences flanking the biconditional is the sentence A, then you are licensed to infer the other sentence flanking the biconditional, in this case B, and justify this inference by citing the rule biconditional elimination as applied to lines M and N. So here are a few examples of correct applications of biconditional elimination. If in line M of your proof, you have the biconditional A if and only if B, and if in a different line of your proof you have the sentence A, you can infer B. Here's a somewhat more complex example. If in line M of your proof you have a biconditional of the form A or C if and only if B, and if in another line of your proof you have the sentence A or C, then you can infer B. Now, the order here again does not matter. If in line M of your proof you have the sentence A or C, and in a later line of your proof you have the biconditional A or C if and only if B, you can infer B. And to give you a final example, suppose that in line M of your proof you have the biconditional if A then B, if and only if C, and in line N of your proof you have the conditional if A then B, then you can infer C. Biconditional introduction is very similar to conditional introduction. The basic idea is this. If under the supposition that P, you can infer Q, and under the supposition that Q, you can infer P, then you can conclude that P if and only if Q. So for example, suppose that Atari is to the right of Co. You can infer that Co is to the left of Atari. And now suppose that Co is to the left of Atari. You can infer that Atari is to the right of Co. So you can conclude that Co is to the left of Atari if and only if Atari is to the right of Co. Formally speaking, biconditional introduction makes use of two subproofs. The rule looks like this. If under the assumption that A, you can infer B, and if under the assumption that B, you can infer A, then biconditional introduction licenses you to infer that A if and only if B, and you can justify this inference by citing biconditional introduction as applied to the two subproofs, the first one from M to N and the second one from M prime to N prime. So here are two examples of correct applications of biconditional introduction. First example is similar to what we have just seen. If under the assumption that A, you can infer B, and if under the assumption that B, you can infer A, then you are licensed to infer that A if and only if B. To the right, you see a somewhat more complex example. In line M, we introduce the supposition that A or B. And suppose that under this supposition, you can infer that if C then D. And suppose furthermore that under the assumption that if C then D, you can infer A or B. Biconditional introduction then licenses you to infer that A or B if and only if C then D. And you can justify this inference by citing biconditional introduction as applied to the two subproofs, the first going from line M to N and the second going from line M prime to N prime. Here's another example of a Fitch-style proof that illustrates the use of biconditional elimination. So we want to prove the conditional that if S and T, then T and R, from the assumption that S if and only if T and R. And as always, I've put the premises of my proof at the very top, drawn a Fitch bar underneath it, and I've put the conclusion that I want to establish at the bottom of my proof. So how can we prove this? Well, I observe that our conclusion is a conditional. And that suggests to me that I will be able to prove this using conditional introduction. And conditional introduction requires me to set up a subproof. So conditional introduction goes like this. If under the assumption that S and T, I can infer that T and R, then conditional introduction allows me to infer that if S and T, then T and R, citing conditional introduction and the subproof from line 2 to somewhere. Now I'm going to put a question mark here to remind myself that I have not actually established T and R yet. That's on my wish list. I haven't actually proven this yet. Okay, so that's where we want to go. We want to establish T and R. Now let's look at what we have. In the first line, we have the biconditional S if and only if T and R, and in the second line, we have the conjunction S and T. Now I am just gonna go ahead and infer both S and T from line 2, citing conjunction elimination. Now we have inferred both S and T, and now I see that in the first line we have the biconditional where one sentence flanking the biconditional side is S. And I have established S in line 3. So that means that I can infer T and R, the other side of the biconditional, and cite biconditional elimination applied to lines 1 and 3. And that's awesome. So I have inferred T and R, and that's exactly where I want to go. So I could either erase this line here, it's redundant, or I can just justify it, citing the rule reiteration and line 5. And now I just need to fill in the blanks. In line 7, we have our conditional, and I'm now able to infer this or justify this inference, citing the rule conditional introduction and the subproof from line 2 to 6. So let's sum up what we have done today. Today, we got a first introduction to formal proofs. So we started out by discussing what formal proofs are, and in particular, what a natural deduction proof system is. We then studied 3 pairs of inference rules, namely conjunction introduction and elimination, conditional introduction and elimination, and biconditional introduction and elimination. And while we discussed these rules, we came upon 2 important special topics. First, we noticed that there's an important concept of sameness of form, and that the ability to identify sentences of the same form is crucial for the correct application of any of these rules. And then we also saw that some of these inference rules rely on the use of subproofs, where subproofs symbolize the introduction of additional assumptions into your proof. And to be able to apply subproofs correctly, you need to obey a couple of important constraints. In the next lecture, we are going to add to this stock of inference rules and learn introduction and elimination rules for the remaining connectives. And then we are also going to discuss important proof strategies that are going to enable you to construct complex proofs independently.